session. So it's mostly about data to support space resources, activities, and space exploration. So what do we need to gather in terms of data in order to enable the further steps? So I welcome here the first speaker, which is Chen from the Technische Universität in Berlin. And I see that this session will put my pronunciation skills to the tests with all the interesting names. So please, floor is yours.
Hello, everyone. And my name is Chen, and I come from Technische Universität of Berlin and planetary geodesy. And today, we are here to introduce our recent research to you. And the topic is a new machine learning technique for image-based topographic model retrieval at high speed, quality, and resolution. Firstly, please let me introduce topographic model to you. And topographic modeling is the process of creating a 3D representation of the moon's surface. This is generally derived from images or laser altimetry. It is a fundamental data, essentially high-resolution model to support some scientific research or engineering tasks, for example, landing site selection and illumination analysis and resource exploitation. But currently, high-resolution lunar topographic model is extremely coverage spatial limited. We think there are two reasons. Firstly, not enough stereo images for SPG method. And secondly, for the single view methods, for example, cephalon shading, it is extremely time consuming. For example, let's see this picture. It shows the image-derived high-resolution model by SPG method marked by the red pixels. We can see it is really extremely spatial coverage limited. Okay. And so therefore, we want to use single view images based on machine learning technique to explore an efficient topographic model retrieval method. We think our work has three contributions. Firstly, high-quality retrieval of multi-scale terrain features, including irregular features, for example, ejecta rays or boulders. And secondly, good performance in areas with large elevation relief. And finally, our method is with high processing speed. Here is the 4 Nauk images, to test the methods. And we can see this area are with different height differences and shows different typical features. Here is the recovered DTM by hour and by SPG. SPG method is a very reliable DTM topographic model. Topographic model equals to DTM. And the reconstructed topographic models of us is very similar with SPG methods. It shows our is reliable. And but our results are with high resolution. For example, the crater with 500-meter craters, the diameter is 500 meters. And we can see our results shows more small-scale craters. And for the SPG results, it also shows the mosaicing artifacts caused by different image pairs, but our results is our results are artifact-free. And in the B1, it shows dune-like terrain features. We can see both methods are similar, and they are consistent with the original Nauk image. But it is in 8 kilometer and 8 kilometer area. When we focus on 1 kilometer and 1 kilometer area, it shows the elephant hide features. From the results, it is clear that SPG methods are with artifacts, but our results can show these elephant hide features clearly and consistent with the original Nauk image. It's some examples, but and it shows the same advantage of our method. But what I want to point out is in area B2, it shows subtle ejector rates of the crater. And in this local area, we can see our results can capture these subtle features, but SPG methods cannot do it. We also compared with the latest machine learning methods because our method is machine learning methods. And compared with the recent methods, our results shows the best accuracy across all test area and across all metrics. And for this metrics, it is explained in Liu 2022. And we also use the hair-shaded map to compare the details. We can see in the crater with 550 meters, Chen 2022 shows clear artifacts, but this study, Chen 2022 is my previous work. But our recent work is consistent with SPG and Nauk image. And for the features marked by ellipse or circles, we can observe my previous work is not consistent with the Nauk image, but currently we can do it. And in the last panel, it shows the elephant hide skin again. And SPG and Chen 2022 method shows different type artifacts, but we are artifacts free. And I also compared with another group. Just from the topographic model, we can already check Tau 2023 cannot recover the topographical model correctly. And as marked by the yellow arrows, there are 4 craters can recovered by reliable SPG method and our method, but Tau 2023 cannot do it. And I also compared our results with differentiated method. It's a very reliable. It's also a reliable and a well-established method in my field. And we compared these 2 methods we compared this using 2 methods covering the same area, but with different illumination conditions. We can observe our results also achieve better accuracy than differentiating. And of course, we still need to compare them using the hair-shaded map, but now I used the cross-illumination verification to test both methods on 2 local areas. It is very clear, and our results is robust and consistent on the different illumination, but differentiated method is affected by the illuminations. Last but not least, what I want to point out is the speed, processing speed. For example, in this area with 114 square kilometer, we can derive this high-resolution DTM in several minutes, which is 65 faster than Chen 2022 and 850 times faster than differentiated method. So we proposed an efficient machine learning methods for high-resolution, high-quality topographic model reconstruction at high speed and high resolution. This brings the hope for large and even global area high-resolution terrain reconstruction. And in the future, we also will focus on 1 meter resolution topographic model reconstruction on the South Pole region. And we think it is more interested in our community. And actually, we already can derive very good results in the illuminated area in the South Pole region. Thanks very much. And here is my email address. And this website is hosted by my colleague, Dr. Philipp. Dankeschön.
Thank you very much. Are there any questions from the audience? I see none. Maybe I have a question. Have you considered applying this as well to multispectral or hyperspectral images?
I want to, but currently I also use our methods to derive the Chang'e 2 images. And it's also very good. But other images, no.
Okay, that could be an interesting future application. And maybe another question. Are there any ideas or thoughts about implementing this, let's say, on board? Or is that, in terms of computing power, too demanding, for instance, for an OBC, for an onboard computer, to get, let's say, not in real time, but let's say compressed already high-quality images from an orbiter, for instance? Is that something you consider feasible, or is the computing power too high, which you need for
currently, yeah.
Yeah. Okay.
Yes, currently, yes. Yeah.
Okay, thank you very much. So another applause for Hao. So the next talk is about from Abigail from ESRIC. Calzada Diaz, I hope I pronounce it the right way. And she's speaking about the descriptive models of lunar high titanium deposits. So we're getting back down to the moon.
Thank you. Okay, thank you. Good afternoon, everybody. So I'm going to talk about models, descriptive models for some specific type of deposits on the moon. So I'm sorry, because in this talk I'm going to have some definitions, because I think that it's very important that all we know agree in what we are talking about. So the first definition is like, what is the difference between what is resource exploration and what is resource assessment? So the resource exploration means to discover new deposits that we didn't identify before. But when we are talking about resource assessment, we are focusing on estimating the size, the quantity, and the quality of deposits or potential deposits that we know or we have some certainty that exist on the moon. So usually for the resource assessment, here on Earth, we follow this type of diagram that we see there. So we start seeing what type of individual deposit exists and seeing the main characteristics of the deposit. Then we group it in deposits that are very similar, and then we start to create these models. The first part is like the descriptive and the genetic models. So a descriptive model is just arranges the information in a way that describes the properties of the deposit. It's just what we see. This is what we see on this deposit. A genetic model is a theoretical model. So it says like how this type of deposit it was actually created. So during my work, what I focus is in the first part, in the what. What type of deposits are there? What are the main characteristics that allow us to group them? And how these deposits were formed. So I focus in ilmenites on high titanium. So it's like, why in ilmenite and not in another type of resources that actually many people talk about? So, well, the high titanium deposits are really important, especially the main resources could be ilmenite, but it's not the only one, as I'm going to mention later. And the main use that we are thinking about is oxygen, extraction of oxygen from this ilmenite. So first, it's like we know we have some geological certainty that ilmenite exists on the moon. So we have remote sensing data that we want, the map that we see here, that it measures titanium. And usually the carrier of titanium is this mineral called ilmenite. That is an oxide of titanium and iron. But not just that, we also have samples. We have samples brought from the Apollo missions, especially the Apollo 11 and the Apollo 17 missions, that they bring samples that show that this ilmenite exists. And it has actually titanium on it, but also we have meteorites that contains ilmenite and high titanium glasses, so it's like, yeah, it exists. We have some geological certainty about that. But also, it's because it aligns with current research that is being done at ESRIC. So we have several projects that are related to the extraction of oxygen from this ilmenite. So for example, we have one that is the plasma-enhanced hydrogen reduction of regolith that my colleague, Marco, is going to talk more on Wednesday. And also we have a fluidized bed hydrogen reduction of ilmenite that is a project that we do in collaboration with ESA. And we have also the purification of the commodity that is extracted from this ilmenite process. It's a poster by my colleague Igor that I invite you to all go and see it. So actually, it's like we have this alignment of what ESRIC is doing and actually the geological certainty that it's about that. But when we talk about resources and when we talk about how they use resources, we are not just talking if it exists or not exists. It has to exist, yeah, but also we need to be able to extract it. So I'm using terminology that is being commonly used on terrestrial resources, but it has slightly modified for lunar resources. So I also invite you to check this paper from the USGS, the Assessment of Lunar Resource Exploration in 2022, that is really, it explains all the definitions that actually I've been using here. So, well, we talk about what is technically recoverable. So we limit the consideration of if a resource can be extracted for technologies that are available, hopefully will be available at commercial scale production in the next 30-year time frame. This type of definition is actually is the definition that is used in the oil industry. So usually when we talk about oil deposits, we think it's like, okay, it's this oil, we can recover this oil in the 30-year time frame, so we are using the same type of definition in this case. And also the definition of reserve, probably many of you are very familiar about this definition of reserve that is like what it can be economically feasible. So actually it's like that type of resource of deposit that you can extract some kind of economic benefit. What's the problem? The problem is like on the lunar resources, the market forces are still not well understood. So what we decide is like, okay, we are going to consider a reserve like the conversion of a commodity that is not just technically possible, that just not we have the means, but also we can achieve it within the mission constraints. So the mission constraints is like the mass, the power, the budget, and all this kind of concepts that are commonly associated with the space industry. So, okay, what about the high titanium deposits? So I want to be clear that when I talk about high titanium are those areas of the moon that have a content of titanium over 9 weight%. In lunar mare, usually is the lunar mare high titanium mare regolith, mare basalt, sorry. So it's like, okay, what is the situation right now of these deposits? So as I mentioned, we have some certainty that these deposits actually exist. So we say like it's measured. It's measured in the sense that we detect them. And actually, I was able to figure out which areas have over 9 weight% of this titanium. But it's like, can we really recover at a commercial scale right now? It's like in the lunar surface, it's like, okay, right now, no. But hopefully, and I hope so, definitely I see as all the talks and conversations that I'm having during the Space Resource Week and with other colleagues, it's like definitely in the 30-year time frame, we will have the technology to recover these resources from the lunar surface. So it will be considered a high titanium reserve. So this is a first preliminary map. I use several data sets to create this map. And what I focus mostly is like, okay, I look at the surface, because unfortunately we don't have that much information about what is below. It's like, I'm going to look at the surface and see what type of geomorphological features are there that can tell me what actually is the protolith, the original rock from where this regolith created. So based on that, I use several types of data sets. And I checked several deposits, and I grouped them in 4 types. The one is the typical mare basalts, high titanium mare basalts. Then I have atypical high titanium mare basalts, the pyroclastic deposits, and a crater interior. The crater interior is an area that on the surface doesn't seem that there is any high titanium, but when impact, it excavated areas with high titanium. However, I'm not going to focus too much in that one because there is only one location that actually can be identified as a crater interior. That is the Janssen crater shown in green in Tranquillitatis. So, okay, typical mare basalts. Typical mare basalts is what we have all in mind when we're thinking about mare basalt. It's like this kind of coherent basalt, like with olivines, with pyroxenes, with plagioclases, and with ilmenite in this case. So we see in that image of a microscope sample, it's a sample from the Apollo 11, and we see what it would be the original rock of this type of basalt. So we see these relatively large crystals. They are not super large, but they are quite large crystals. And we see the crystals of ilmenite that are the ones that are shown in black. So this was the typical one that we have all in mind, that we see many times in all the Apollo region. So it's really easy for us to understand what is going on there. However, we have the atypical mare basalts. For these are areas that actually there are geomorphological surfaces that are quite strange. One is called irregular mare patches, and others are domes. I'm not going to get into the geological thing here, even though I would love, but I don't think we have time for that. The thing is, like, this type of original rock, it's slightly different to what is found in typical mare basalts. For example, we see here this image of a rock, and the first thing that we see is like actually the grain size is much more smaller. It's like very different. It's very small. And also we see that they have a lot of voids. There are a lot of hollows in that thing because it's a material that is highly vesicular material. This was formed it's supposed that it was formed in a very similar manner that it happens in Hawaii or in other volcanic islands when you have some kind of basalt that in the middle gets basalt with some more volatiles, and the volatiles get out. And in the moon, it forms these irregular mare patches or these domes when they don't extrude. And yeah, it's highly vesicular. So as we see, this is a much more complex area, and this is widely seen in Tranquillitatis, in North Tranquillitatis area. And also we have the pyroclastic deposits. The pyroclastic deposit is like when you have a volcano, it's like the first thing that came out. It's like lava fontaines. So as we see here, these orange glasses for the Apollo 17 landing site. And what we see is like first, when we see it in the microscope with the when we see it we see that it's black when the polarized is cross. That shows that actually they are not minerals, they are glasses. The glasses, the difference between minerals and glasses is like the glasses doesn't have internal structure. So actually it's a very different type of material than what we are talking in the mare basalts area. And probably this is going to be mixed with other type of regolith that came from ejecta from other places, and also with other type of ilmenites maybe they are going to be there, but still is pretty different. So obviously, one part that affects the regolith formation is like the original rock that it came from. So it's like, we cannot expect that the same type of regolith is going to be if it derives from a rock that is big glasses, very coherent, or if we have a rock that actually is small glasses, small crystals or minerals, and there is a lot of voids. For example, when in a normal circumstance, we will see something very, as we can imagine, like boulders, rocks, agglutinates. But in the case of the atypical mare, probably the impacts, the first thing that they are going to do is not actually break the minerals. Probably it's going to crush the voids. And also because it's a very, the substrate is so porous, maybe some agglutinates that are very fine-grained are going to migrate towards. So actually it's going to be very different type of material that is going to affect the subsequent process of excavation, but especially of beneficiation and extraction processes. So yeah, so titanium deposits on the moon were detected already by missions that they were not originally intended as a resource. They were a scientific exploration, but they were used as an exploration for resources indirectly. So, however, that is not enough. There is still, we need, for doing a proper assessment, we need to have more details, a lower scale of what is going on in these different type of deposits. So we need high-resolution instrumentation of our orbiters. We need also surface exploration, surface prospection using robotic platforms and different type of instruments. And we need drilling. That is like the key thing that we do in exploration of resources on Earth. So finally, it's like I want to say a couple of things that for you to remember. So it's like, first, it's like, well, what is a descriptive model? A descriptive model is a structured approach that helps to understand what is going on, the unique characteristics of each lunar deposit type. The deposit of this type of models are the first step to a proper lunar resource assessment. So if we don't know what we are going to find there, it's really very unlikely that we can continue to know how we are going to extract it and how much we can extract from there. And also I want you to know that even although we see this map with the high titanium material, that is like not all are the same. Even although we have exactly the same amount of titanium, we don't have exactly the amount the exactly same type of material. So yeah, identify three main types of deposits for high titanium, that is the Maria, high titanium Maria, pyroclastic deposit and crater interior, but still we need more work to be done on this. And with this, sorry it's too fast, it's like I wanted to really be sure that I can say everything that I had in mind, but anyway, I will be around if you have any questions or more detailed questions about the geology or whatever, you can just see me around and ask me around or ask now. So yeah, that's it from my side. Thank you very much.
Thank you very much. Are there any questions? I see there's a hand rising, so the floating microphone finds its way to you right now.
Thank you very much. Hello, my name is Martin from Light Curve Films. So thank you very much for your talk. Just a curiosity. So the determination of titanium oxides is through spectral determination, I guess. I didn't see any spectra. But how certain or how degenerate are those? Are other species also, in the spectral area, spectral range where titanium oxide is, detectable? Are other species also present? How do you separate those?
Yeah, that actually is very tricky. I mean, these maps, the maps that I show is actually derived from hyperspectral and other type of data. But actually, ilmenite is not the only material that can have high titanium. There are other minerals like armacolite, for example, that also contain some amount of titanium. And that is a really good question because it's a tricky thing to do. It's like, and we need to actually get samples to be sure how much actually is like, what is the percentage of actually this mineral and this other mineral? And that is something that we don't have enough information, actually, yeah.
Yes, thank you very much.
You're welcome.
I see there's a question from online from Ebert Pogundke. He's German, but still a challenge for me to pronounce it, so sorry for that. He's asking, ice has already been detected at the poles and has confirmed the theory about having ice on the moon. Because of the diversity of minerals, in addition to hydrogen and oxygen extraction, the Aristarchus area seems to be more interesting and for exploration. What do you experts think about that?
I mean, the poles of the moon are not just interesting just for the possibility of having water ice. The thing is, like, for example, in this case, when I was in the situation of having to decide what type of deposit I will start doing, it's like I decided to start with titanium for something very simple. It's like we have more data. From the lunar water ice deposits, we know that, we have some indications that, definitely there is water ice there, but actually we don't have that much data, we don't have that much samples as we have for the titanium kind of thing. So right now, we need definitely more data from the poles to actually know more about the water ice in the poles to start doing the descriptive models. For right now, we don't have enough geological certainty for knowing how to do these descriptive models of water ice.
Okay. Yeah. Thanks a lot. Again, applause. Thank you very much. So we are slightly overrun, but nevertheless, now the next talk comes from my colleague from ESA, from Igor Drozdovskiy. Very good. And he's talking about the identification of minerals with the Pangaea analytical toolset. So go on a journey with Igor.
Thank you. Hello, everyone. I'll try to pronounce my name properly. My name is Igor Drozdovskiy. I work as an expert scientist at European Astronaut Center in Köln. And my main role there, I support the development of Pangaea analytical toolset, which is a topic of this talk. So the goal of this project, as you can probably deduce already from the title, is to develop the software and hardware tools for the real-time in situ identification of geological materials. So this is a team's effort. I'm only supervising some of the development, but our team consists also from the scientists, developers for software and the hardware. We also have instructors and also the specialists on the support of ground and operations and also the space operations. And why it's important? Because in this project we are focusing not only on the hardware or software identification, we are also focusing on how to deliver this information to astronauts on the field and also deliver the information which is a human understandable, quickly understandable, but also not only for astronauts on the field, but also for the science support room. So in our view, inaccurate real-time mineralogical analysis will be critical for future human and robotic exploration of the moon and other planetary bodies, both for science and resource perspective. Besides, we already use actually part of this analytical toolset in the Pangaea geological field training, which is conducted for the astronauts, but also for mission developers. And because we already used on the field some portable spectrometers, and we are able to integrate part of our toolset into the mobile portable devices. So if the data on potential samples is available immediately, we argue that in this case, we can actually simplify the task of selecting which samples can be analyzed later on the ground or in, let's say, in the campsite. This is what we actually had in our objectives since the very beginning of the Pangaea training. Not only training, but also idea of how we can improve future exploration. And human is our main priority, but we are also not forgetting that the robotics probably would be complementing also these explorations. So what we learned from Pangaea is actually one important thing. And that is that the development of this kind of tool set needs to be done together as a tool set. And this is not only our Pangaea training which showed to us. Also, we had a chance to actually follow some ESA and ESRIC supported resource prospecting studies, which also shows that when the tools are developed by different, let's say, partners, very often the final step combining the results obtained from the spectrometers with calibration data and matching this with, let's say, the reference catalogs, and also, in important part, using the machine learning or any kind of mineral recognition software needs to be developed together. Designed and tested together, these tools will provide the necessary accuracy and speed, both in real-time recognition of materials and in sharing of the importance of these discoveries with the field crew and science support rooms. So in Pangaea, we actually address the question of how all these tools can be efficiently used together as a combined tool set, because it's a different perspective comparing to traditional, let's say, robotic missions, where there is a different there is a different time frame. There is a reasonable time for the analysis of the raw data, while, for example, during the surface AVA by astronauts, you're limited in time, and the decision needs to be done quickly and on the fly. And in addition to this, we essentially focused on how to identify in real time hundreds of minerals and composition of these minerals on the fly. So having experience of actively using of these various spectrometers during the Pangaea field campaigns, geological field traverses, we came to the conclusion that in order to accurately recognize as many planetary materials as possible, the combination of molecular and atomic spectroscopy on the same core-line spot would be critical. In fact, ESA actually has already initiated a development of such combined portable spectrometers with the help of the industrial consortium led by Instituto Nacional de Técnica Aeroespacial INTA, that is funded under the ESA expert budget. And there is a poster presented by this consortium, Phoenix for Pangaea, by Andoni Maral and the collaborators. I invite you to look on it. So the role of the Pangaea team in this development, we are supporting this development with calibration data, validation samples, and also the machine learning software, which help explorers to interpret the recognition results. One of the key assets, I would say, of the analytical tool set, and this is where we started, is actually in Pangaea mineralogical database, that includes the reference information. First of all, it has a catalog of petrographic information on all currently known minerals found on the Moon, Mars, and other planetary bodies. And in addition to this, it also has archives of reference spectra for all these minerals. So the petrographic catalogs contains only essential information and required for the rapid mineral identification. Some of this actually listed on this slide. And also, it's also add one part that is not necessarily always present in the catalogs. We also added a very short description, something like a Twitter message showing the importance of these discoveries. This is the meta-information that would be displayed together with identification of the minerals, helping astronauts in the field quickly realize why this mineral could be important, or this composition can be important for either for the exploration of geology or for in-situ research utilization. So in terms of the spectral archives, which we collected, it's based on actually on both types of research. First, it's a bibliographic study, and we collected thousands of spectra from open access archives, both for molecular spectroscopy, and for molecular we focused on two methods. It's a reflectance, visual near-infrared or short-wave infrared spectroscopy, because there are already plenty of instrumentation which allows to conduct these measurements. And the second one is Raman spectroscopy. It's a very powerful method also to identification of different molecules, including minerals. In addition to this, we also collected the spectra for the X-ray fluorescent and LIPS, which is laser-induced breakdown spectroscopy. These are two complementary spectroscopic methods which are very helpful in identification of chemical compositions of elements, not necessarily knowing what the mineral molecular structure, but it understands very well what's the composition.
So the spectral libraries for atomic spectroscopy is actually very limited in terms of not many minerals are lacking of this data. And what we did, we also created synthetic libraries, which allows us to use all this data set as a training for the machine learning model. And we are using both the real spectra and the synthetic spectra as a training data set for calibrating, or let's say for creating of machine learning classifiers. So we based our mineral recognition on the machine learning classification techniques rather than, let's say, on the classical spectral correlation methods with reference spectra. Because of versatility of machine learning models, we can work with different types of data. And for us, as I mentioned at the very beginning, we are very much convinced that the combination of atomic and molecular spectroscopy can achieve a better accuracy and classify more minerals. Therefore, we also started to think about on supervised classification as a first step, and that is already results that we published in 2020 and 2021. We realized that supervised classification is not only the type of classification we can do, because you are limited only for the known labels, and we expect to discover some new minerals perhaps we are not really finding very often enough. Therefore, we also added incremental learning in the last years, and we are also working on the few shots incremental learning is in our current state. So, but what is the most important, and I mentioned it at the beginning of the talks, we already have not only machine learning model which are running on very powerful laptops, we also exported these machine learning models and the reference libraries onto the portable computing device such as electronic field book. Electronic field book is another project which is also being developed by our team that allows to combine the data from different sensors, and also we are using it for Pangea training because it allows in real time an exchange of all the information which comes from individual, let's say, explorer on the field and science support room, and also track every single data collection in real time. So we were able to export machine learning model, and we were testing this already during the Pangea training in the last couple of years, and the last year was particularly very promising results. So to summarize, the Pangea analytical toolset combines, developed together, three major elements. First of all, it's a mineralogical database, which contains catalog of reference information on known planetary minerals. Second, we have collected for all of these minerals as many spectra as we can, including real spectra, but also synthetic for some, missing one. And you can see on this slide we are having about 640 minerals in our catalog. And then we, for all of these minerals, we collected for both for the Raman and visual near-infrared spectroscopy, about 10,000 spectra. Much less for XRF and LIPS, but we also go into the numbers now, it's 1,000 about. And finally, we also have developed our own machine learning pipeline, machine learning framework, which allows to classify the data based on the data fusion, essentially a combination of molecular and atomic spectroscopy, where the machine learning classifier is focusing on molecular spectroscopy from the Raman and the visual near-infrared data, and add, let's say, in additional information and additional weights when we're adding an atomic spectroscopy. And finally, what we also were able to do is actually not only working on individual, let's say, pure minerals, we also used now machine learning models in order to do spectral unmixing. And as I said, we already have a field test, and the accuracy that we actually shown on this plot is more or less convincing us that our initial assumption that combination of two methods is better than one, it's expected, but it's good to see real numbers. And finally, this is always work in the progress. What we are trying to do in the next phase is when the instruments which are developed for us will be
already finished, which I hope it will happen actually by this summer. We will start using these instruments to get more spectra and test our pipeline and the whole analytical tool set. If you have any questions, and please just don't hesitate to ask me, and this is my email. You can also always contact me. Thank you.
Applause for Igor. Thank you. Any questions? There is somebody in the back to the left.
Okay, thank you, Igor, for this interesting talk. I was just interested in LIBS because we are trying to also do in this way. Basically, did you simulate conditions for lunar or Mars conditions for your LIBS? Because this is something that significantly affects your plasma, and I'm just curious what simulation you did in terms of atmosphere.
Yeah, so at this moment we are not trying to actually even obtain the real-world spectra on any of the, let's say, planetary environment conditions, so the temperatures, atmosphere, but it's the next step. What is important is that the machine learning model we can quickly reclassify as soon as we'll get a new data. Maybe even in the new facilities which are open, we will be able to obtain the additional reference spectra. And for the LIBS, I think we just used mostly of synthetic spectra, assuming some possible conditions, and the real-world spectra was in laboratory conditions, so they will need to be reassessed when we will get a proper, let's say, vacuum chambers or the chambers which are thermally similar to the moon. But again, for the daylight or night, it depends. So we will get two sets for sure of the spectra.
Okay, thank you. Any more questions? If not, I might have one.
Yes.
You somehow touched on that already, you know, the issue with so far building up the library, making the machine learning with pure minerals. And indeed, it was one of my questions, if, for instance, within the focal plane of your Raman laser, you have a mixture, let's say several grains, a mixture of different minerals. So what is the robustness of this method in this respect? And is that something you're working on? Yeah.
Unfortunately, one of the problems, you mentioned Raman, is that the most famous database roof is created for the pure minerals. For reflectance spectroscopy, for example, we actually have a data set specifically created for with known mixtures. So I cannot give you specific numbers, but we were able to recognize, let's say, when there are 2 or 3 different minerals contribute to the spectra in the reflectance spectroscopy with accuracy about 15% of real abundances. So I think it's quite a good number, even comparing with not machine learning methods like the Hapke model and so on.
I know a group in Norway has been working specifically on FTIR spectra in order, this was more for gas analysis though, to actually, when you have a multi-component mixture, to still, let's say, deconvolute the spectra such that you can discriminate the different components. So maybe it's something to think about what kind of algorithms we're using to do that. And maybe eventually, if that is possible, to apply this to Raman as well.
For Raman, yes, yeah. Absolutely. Yeah. And actually, we already have that as a development branch.
Okay, good, very good. Thank you very much again, Igor.
Thank you.
So the next speaker is, now that's an easy name, Philipp Reiss. So from University of Munich, and he will take us on a journey on some instrumentation-related aspects. So instrumentation for the mobile in situ detection and characterization of lunar water.
Thank you, Robert. Some actually do manage to pronounce my name wrong, so happy you didn't. Yes, so although this is a session on data, I'm sorry I will not present any data today, but I will talk about the data that we need in order to enable the whole space resources well, topic around the moon, right? So, and to start with, what we're currently missing, and please ignore the typo here, is the ground truth for, in particular, the water that we're after currently with the prospecting missions that we will see within the next 5 or 10 years. The main questions that we need to answer with these missions by delivering the ground truth is to constrain our current estimates of concentrations, quantities of the lunar water, but also the locations where we might find lunar water, and how they vary across the surface, across the depth, and across, well, over time, basically. So these questions are still unanswered. We just have hints and basic evidence of lunar water so far. So I think we all agree that we need this ground truth to better constrain our models and to learn where we need to land and where we need to go and mine and produce products from this resource. Of course, the origin also needs to be determined in order to understand how the water migrates across the surface, where it actually comes from, and in which form it is. Well, when going to the surface and exploring the water in situ, there are basically two typical approaches for sampling, and there's a typical trade-off between coverage and resolution. So mobile instruments that provide a great coverage and that mapping capability that we need in order to well, approach mining and operations later on, typically don't bring the resolution that we have in order to determine things like isotope ratios, right? And then the instruments that are stationary, or the instruments that we even have on the Gateway or here back on Earth that require some return, they come with this resolution, but they don't provide the coverage because they're either stationary or from an individual location. So we have this typical trade-off that we're working with, and then we also have something to consider when exploring the lunar water, which is the loss of this highly volatile material. So we need to bring the analysis to the sample and not the other way around. So the charts here that I have on this image, just to complete the slide, are just showing you the vast variety of different forms of water that we expect to see, and also the vast differences in scales, ranging from nanometers or molecular scale in the exosphere and as loose as orbits on the surface of the grains, up to kilometer-sized, or maybe less than that, but hundreds of meters-sized larger deposits in the subsurface. The bottom line is we don't know. So to learn more about that, I will briefly introduce a couple of instrument or sensor developments that we're currently doing, that we're currently working on, that address these topics on different scales and with different types of coverages and resolutions. So the first thing here that we've been developing for the last 12 years or so is what we call the Lunar Volatile Scout. And this is basically an instrumented drill. It's really small, it's about this size, fits on a small rover. And well, this drill comes with a heating element and a mass spectrometer. So it is able to actually bring the analytical capability directly to the sample. We do not need to excavate a sample. We do not need to touch the volatile material. So we can really minimize the volatile loss and therefore get the most out of our measurements. On top of that, it's a mobile approach, so we can put this on a rover, as you see on the image here, and we can, well, measure along the traverse, measure at different times, with the constraint that we can only access the shallow subsurface. Okay, so there's the trade-off, again, in a different form. The current development stands, as you see here, so this is the result of a phase A development that we did for ESA a couple of years back, and we're currently working on an improved version of the mass spectrometer, and I point you to the poster here on the lower right of my colleague Victoria Levy of the Open University, who's presenting a miniaturized mass spectrometer for that application on her poster. So here, as you see, the primary goal of this instrument is detection, find out whether or not there is water with a limited approach to the quantification. So we cannot necessarily do isotope ratios with that. instrument, but we can easily detect how the water behaves around the landing site, in front of a boulder, behind a boulder, so how it's moving with a shadow in the shallow subsurface, how it's behaving or how it's distributed in front of a PSR, but also inside a PSR. So this spatial and temporal coverage is really the selling point here. Moving on to something even more, let's say, close to a launch or to a flight is a rover permittivity sensor. So this sensor we're currently developing with ESA in preparation for a commercial rover mission. And the permittivity sensor measures the dielectric properties of the soil. With that, we can derive the soil porosity, but also, well, generally speaking, density changes in the soil, and we can also detect water by carefully analyzing that data. So we mount this sensor here, or two of them actually, on a rover wheel, and while we're roving along the traverse, we can stop very shortly, very briefly, and do a measurement and continue. And by that, we can really easily detect volatiles, namely water in the mixture with the regolith. The diagram that you see here just depicts the very simple physics of this measurement. So the regolith comes in sort of a combination of three different materials. The first material is the regolith itself. The mineral doesn't really matter in that case. Water ice and vacuum. Excuse me. And in that end member diagram, basically the mixture that we will find on the moon will be anywhere in this diagram. And depending on the combination of these three end members, it will exhibit a different permittivity, which we will detect. And also by running another analysis in the frequency domain, we can really say whether or not there is water present. So this again comes with great spatial and temporal coverage. It's very limited to the first top centimeters of the subsurface, and it's more of a yes or no experiment, and with the potential capability to derive a quantity of water ice in the subsurface. Something that is very similar to that and is currently basically in the manufacturing phase for the instrument package prospect of the European Space Agency is another permittivity sensor. So this time it's not mounted on a rover wheel, it's embedded in the drill of Prospect. So Prospect takes samples from up to a depth of 1 meter and transfers them to a gas analysis package where basically we can run evolved gas analysis in small sample ovens and with 2 mass spectrometers on board. So this is a very sophisticated instrument package that can provide really accurate measurements. Apart from the gas analysis, which I will talk about in the next slide briefly, we have this permittivity sensor. So this is also in the drill. It will sense the material as we go down, so it will provide us a 3-dimensional electric imaging of the subsurface. Again, it's more of a detection capability to say whether or not there is water ice present. This is particularly important because along the sampling chain of this very complex instrument, we anticipate a loss of volatiles. And the permittivity sensor allows us to measure the soil in situ in its more or less pristine state, so we can quantify the volatile loss along the sampling chain, ideally. And therefore, this also helps to interpret the gas analysis measurements further down the the sampling chain. Again, as you see here, I don't want to neglect the plot that I present here. So this shows you the different dielectric permittivities of different material. And while you see the vacuum, the first end member is, by definition, it's 1. Regolith is somewhere in the medium range, and then water ice is really up there an order of magnitude higher. So this tells you that it's quite easy to distinguish water when it's present. So the second part of the Prospect instrument package, and just a note here, the lander that you see is not the lander that Prospect will fly on. Prospect will fly on a CLIPS lander. The time frame we expect currently is 2027. But it has this gas analysis package, and this really allows us this very detailed measurements to determine basically where does the water come from, right? And all the other volatiles. So it's much more sophisticated than these simple experiments or simple sensors that I just presented. The thing is, it's very, very limited. It can only operate at the landing site with all the implications that there are in terms of contamination of the landing site by the landing engines and so on. But it has this high resolution capability. It also will provide potentially one of the first ESRIC demonstrations, namely hydrogen reduction of regolith to produce water in situ, just as a side note. And yeah, as I said, this is, of course, a non-mobile instrumentation. And then to basically wrap up, we still need the simulations to complement all the in situ data that we will get in the next years, over the course of the next years, in order to extend that data to a broader scale. So local measurements can be extended to a regional and global scale by really modeling and understanding what is depicted here. And this is not my image, that's a great image, by the way, by Caltech. It depicts the lunar water cycle. And or the lunar water cycle as we expect it to be as of now, because we're not so sure about all the processes involved here, and even more so for the actual reactions that go on the lunar surface here. So in order to interpret the in situ data, this will feed into simulation models, and I'm just saying with this slide that we need this simulation capability also to cut through all the scales and to make the most out of these measurements and improve our understanding of the lunar water cycle. And with that, I'm looking forward to that new data, and thank you very much for your attention.
Thank you very much, Philipp. Any questions? I see no questions. That's a pity, because we have some time. So 2 minutes, 2.5 minutes left. Maybe if I may, there's something. Somebody has a question, so where's it?
Yeah, can you hear me?
Yes.
I'm wondering how you actually do the test in ground facilities, because you are now enabling instruments that are larger than 1 meter, and very few vacuum chambers are actually able to keep with this size of elements and structures.
Yeah, that's right. So, of course, we do testing on a smaller scale for the individual subsystems. That's more or less easy, because everything involving regolith and low temperatures is not easy by definition. But we also do have vacuum chambers that accommodate the whole drill. For prospect, for instance, there's a vacuum facility in Italy that we're using, and this is made to accommodate that drill.
Okay, thanks
Great.
very much. One more question, just one more thing, sorry, from my side. You showed very nice this graph showing the permittivity of water, which is way out, and that's why it's easy to detect. Is there any risk that you still have maybe some sort of matrix effect from something else which may cover this?
Yeah, sure. So that the quality of the measurement requires a really good characterization, because one thing is the contact of the sensor to the ground. This naturally plays a role, but also to really make sure that we apply the right mixing law is also crucial. So the best thing to approach that is calibration and testing.
Yeah. No brainer. Clear. Okay, thanks a lot again to Philipp. And now this is the grand finale. We have now the last speaker, Jakub. And I just lost my script here, so
You don't even try with my name.
Yeah, so
even computers don't do this well, they struggle. So my name is Jakub Ciążela.
Yes.
And I will talk, now you understand why. Of course, I will talk about geology here, and those who are here for the middle session, where the 2 parallel sessions, There were some speakers, Jerry Sanders, also Carr from Johns Hopkins University. They underlined one thing, that geology is actually still behind the technology in our preparation. So I think the market is undersaturated with geologists with us, which is good for me, but maybe bad for you, because now I will swamp you with lots of dirt, rocks, and difficult mineral names. But I will do this gently. And the thing is urgent, though, because we, as our Korean colleagues have shown, actually, 60% of us, more or less, think the exploitation on the moon will start in 5, maybe 10 years. We hope that Artemis will be there in 5 years with astronauts starting to construct lunar bases. Of course, transport from Earth is expensive, so at some point we'll need the resources. And of course, here in Luxembourg, you are the best aware of that. So the ESRIC is the best example, established with help of ESA. And ESA distinguishes 5 resources groups. And what I want to show you, that 4 of those groups occur together, more or less in the same places on the moon, which are lunar maria. And I will start discuss metals. They seem to be the simple, and also Abigail helped with that, with this map. So actually she has shown you titanium. This is iron, titanium is on the next one. You can see we are more or less at the same place. So this is Clementine data from '94, and there was a question, what was the method behind? That was near spectrometry and visible light spectrometry. So those two are, of course, strictly correlated with lunar maria, and of course, as was shown, ilmenite is behind this because this is an iron titanium oxide. So on the moon, ilmenite is quite abundant in basalts, more abundant than on Earth. It can be even up to 28%. So those are those black dots here for these people in the room, you can see, or in the clastic material, those particles also contain lots of ilmenite. Actually, regolith usually has the same composition as the rock below. And ilmenite, though, is important also for other reasons, not only because of metals, but also because of energy and propellants. And why is that? Propellants is simple, because it contains oxygen, but energy requires a little bit of explanation. So this is because the crystallographic structure of ilmenite is the best, the most favorable to capture helium particles from the solar wind. So the vacancies here are more or less of this size, and that's why you have an excellent correlation between helium and a factor dependent from titanium based on the Apollo samples. And helium is, of course, a resource, a fuel of the future. It might be. Tritium is another candidate, but helium is also a strong candidate for various reasons. And that's why the modeled content of helium is more or less, the map is pretty much similar to what was shown for titanium and for iron. But this is not the end of good news. Another good news is that oxides, so ilmenite is an oxide, but oxides co-occur with sulfides. And this is a picture taken from an earth sample because it's nice. So sulfides are those yellow minerals, oxides are gray-bright. But if you look at the lunar samples, you also have this in the low bottom, in the low left image. You can see here ilmenite and troilite. Together, troilite is an iron sulfide, also relatively abundant on the moon. And this is just an example from the Chinese mission, but if you look for the correlation, sulfur does correlate with titanium on this image. So this is a typical situation. And this is great because when oxides contain siderophile elements, so except for iron and titanium, also manganese, cobalt, nickel, also platinum group elements very often. Sulfides contain chalcophile elements, so gold, copper, silver, lead, zinc. So all this is in one place on the moon. This is an excellent news. And sulfides per se are important not only because they contain metals, but as Catherine said in her talk, also because pyrite, which is a sulfide, may serve as a material for solar panels. So we also did some measurements for Taltech in Wrocław when the group was there. So these are those analysis of those pyrites that we use. And sulfur is important for another reason yet. It can be a construction resource because on the moon it's difficult to make a traditional concrete. So instead, sulfur is proposed to be used as part of that. And actually there were experiments showing this purple composition, so sulfur with silicate, with also regolith, is quite resistant to temperature changes and low pressure on the moon. But the problem is those minerals are very difficult to find in the near infrared. So we talked so far only about near infrared here because it's easy. There are many spectrometers, but it's not good for all minerals. So those most important for resources, if you can see sulfides, so pyrite, pyrrhotite, they have flat spectra and also quite similar to pyroxenes, which are very abundant on the moon. And if you look at the far infrared instead, these spectra are really good. So all those minerals, ilmenite and also sulfides have excellent spectral features there in the far infrared. I talk about 20 to 40 microns there. And that's why we've designed an instrument, a spectrometer, to search for those minerals. It was selected as a primary payload for the Polish lunar mission with a scope to search for all those resources, so metals, sulfur, helium-3 and other gases, and maybe even water if we have budget large enough. I'm talking to some representatives of the Polish Space Agency. We can cover also lunar areas and search for water. Also good spectral features around 43 microns, water ice, I mean. So this is the design of the instrument. This is actually published already. So here you can go to the publication, but just an explanation why we can operate with the high resolution, high spatial resolution because this is a Cassegrain system. So we have primary mirror and secondary mirror. Then after the secondary mirror, the signal gets to diffraction grating, and it's separated to different detectors. We can detect several minerals at the same time. And in front of each detector, there is this turquoise collimator. This serves to protect the detectors from the stray light. This is how detector look like. This is provided by Laser Components company from Germany, pyroelectric detector. We already tested them in the laboratory using terahertz lasers, and we've demonstrated that sulfides, here there is an example of pyrite, are well detectable in this range. This is a work where my student Sumit Goski, also present here, contributed a lot. And indoor it's easy, but outdoor tests on Earth are difficult because of water. You cannot measure in this range from satellites. That's why it was always underdeveloped, because of the water interferences. But now, with drones, which can operate from an altitude of 100 meters or less, water is not that problematic. We just lose 20–30% on the transmission. So this is what we already did. We built a prototype, which we fly on drones, and we test this in various Polish mines. We also obtain an ESA Technology Transfer Award for this prototype. And the prototype is actually smaller, so the drone can carry it. It has a diameter of 13 centimeters. The flight version is not yet ready. It will be ready for 28. It's bigger. It has a diameter of 30 centimeters, and it must be ready until 28 for the Polish Space Agency. And we are also as a candidate in one of ESA programs, Lunar Mineralogy Mapper, where we need to deliver it for 29. So thank you very much for your attention, and I welcome questions as there are still 2 minutes.
Thank you very much, Jakub. So I see hand is being raised in the back. Please.
Hi, Carl Hibbets, APL. Very interesting talk. Thank you. A couple questions. One, does that spectral range also have features due to silicate mineralogy, the bulk mineralogy in the surface of the moon? And also, given that the atmosphere is not completely opaque to water at those wavelengths, have you considered integrating your instrument into existing telescopes? Because they tend to be at very high altitude, and the column density of water is much lower at those.
Okay, actually, telescopes are sometimes used, especially space telescopes, to look at asteroids. Apparently, this spectral range is also quite good, because once you are above the Earth atmosphere, you have not so much problems with water, so you can look even into asteroids. And this is actually what Sumit, my student, also did in his master thesis. He did some analysis. And I don't remember the first question now.
Are there spectral features due to the bulk mineralogy of the moon, either the Mare or highlands, that would interfere with the detection of those oxides?
Okay, so the spectral features in the far infrared are so good because you have those bounds between metals and sulfur or oxygen. So these are quite heavy bonds. That's why they have spectral features in the far infrared. And they are the same, actually, on the moon, on Mars, on Earth, and they just depend on the mineral compositions.